So obviously, if we integrate a constant from DC to a megahertz, that is 6.25 by 10 to the 10. And then we want to take the square root. 625 by 10 to the 8th is 25 by, I'm sorry, minus 10 minus 10, 625 by 10 minus 12, 10 minus 6. So the final answer is the RMS noise coming out of this, is 25 microvolts. What did I do wrong, guys? What's the question?
What's the 1 squared?
Oh, well, this is a power spectral density in volts squared. So we want to gain that up by the voltage gain squared. It happens that our voltage gain is unity. And we can say that more generally. Here our transfer function is quite simple. It's only one. It's a unity gain amplifier. In general, since it's a random variable, phase doesn't matter. All that matters is the square of the magnitude of the transfer function. And in this case, our transfer function is just 1. It's a unity gain amplifier. So at any rate, you get about 25 microvolts. So let's set it up a little bit differently. Again, we have our imaginary noise source. And there's an amplifier with a non-inverting configuration and whatever. We make this resistor a ratio of not 100, sorry, 99 to 1, which would give that non-inverting gain RF over R1 plus 1, so 100. So this has a gain of 100. So if we do the same calculation, now we get our input power spectral density 6.25 by 10 to the minus 16 volts squared per hertz. Now times the gain squared, which all of a sudden is 100 squared. But the bandwidth of this amplifier, when set up with a gain of 100, is only 10 kilohertz. And then we take the square root of it. And that gives us a result of I didn't do it. I believe that is our 2 millivolt. I'll check my math. So that's 2 millivolts RMS. And I may have made it maybe not quite 2, but I'm sorry. But that is to say, if we set up this amplifier with a gain of 100, and looked at the voltage at the output of it, the noisy voltage at the output, my bad, it's 0.2 millivolt RMS. 0.2 millivolt It would have an RMS value of 0.2 millivolts. One way to think of that is this would deliver as much power as it's the same power as a sine wave, which has an RMS value of 2 millivolts, so 0.2 millivolts. So if it was delivering power to a resistor, it would deliver the same amount of power as a 0.2 millivolt amplitude sine wave, RMS sinusoid. And a 0.2 millivolt RMS sinusoid is what peak value? 0.2 times square root of 2, right? So about 2.8 millivolts. So that is your noise signal. And if you contrast it with my original example where the gain was only 1, I increased the gain to 100. You get 100 squared here. Your bandwidth reduces by 100. So you actually end up getting 100 times as much noise out of this. Okay? 100 times mean square noise. So 10 times as much RMS noise. So the bandwidth only goes down by a factor of 100 from megahertz to 10 kilohertz, but the gain squared is what gives you your output noise. So that's kind of a real basic idea of what noise is here. So you're going to take this noisy signal out of the op amp, and you're going to put it into your amplifier, and the first thing you're going to do is run it into, well, I already said it, run it into some sort of an amplifier, in other words, to gain it up so it's big enough for the AD to read it. Now, let me give you a few hints. Does the amplifier that you use to gain up, to make this 2.2 millivolt RMS signal bigger, does that amplifier have noise? Yes. But it is way, way, way smaller than that amount there. So if you choose a low noise op amp as your front end gain, you will add tiny amount of noise compared to this really noisy 741. You'll notice I only asked you to measure a noise source that had 0.2 millivolts RMS, right? I didn't ask you to measure a noise source that was 2 microvolts RMS. That would be a much, much taller order, okay? Because that's such a tiny amount of noise, whatever you're putting it into, you have to worry about the noise that system adds. But this is just like my voice in this microphone. You know, it's the amplitude of that signal is pretty big compared to the hissy little noise in there, so you hardly notice it. So that's a pretty healthy noise. So you won't have to worry about the input. I mean, you should mathematically justify that it's not important, but you'll find out that it's not significant. Now, the next question is the next thing down the line, is the A to D. And is that noisy? Yeah. Even though it's delta sigma and they're very low noise, it's noisy too. But once again, remember, this signal gets sent to an amplifier, which makes it bigger. And now you're talking about a signal, you're gaining up this signal to maybe 500 millivolts RMS. And that's enormous compared to the noise of a 24-bit AD. So you don't need to worry about any of the additive noise of your system. So again, analyze it. It's relatively easy to do, but you don't need to worry about this. So as I believe I said last time, just think of this as a signal that's band limited to 10 kilohertz and is no bigger than plus and minus 6 millivolts. And you have to put that into an amplifier to make it bigger so that its amplitude is closer to the input range of your A to D, and then digitize it at 20 kilohertz. 20,000 samples per second. So there's still a couple of questions about the filtering and some things about the low end of the spectrum, which I'll really hope to finish up next Tuesday, and that'll be it. I will hope to show you that this noise power spectral density, it kicks up. So the power spectral density gets bigger at lower frequency. I will show you next time, and you can find it in just about any circuit book that has a chapter on noise, that's relatively inconsequential for our application. So you don't have to worry about that. Okay, so the noise you're worried about is this flat part, even though we said down to 10 hertz. So next time we'll talk about that lower frequency limit and why it doesn't matter. This is called 1/f noise because it's proportional to 1/f. And we'll also talk a little more about some of the features of the 24-bit ADD. Again, if you walked in late, this is the example of the box that we want you all to buy. It costs $6.89. It's pretty roomy, and we have a line drawing for it. So figure you're going to cram your circuit board in there, and it's not a problem. Thank you.